Okay, thank you very much firstly for the invitation, and it's always a pleasure to speak to others. Let me see if I can share my screen. Do you guys see my screen now?
Yes.
Okay, so you might have already seen we do a lot of multi-scale simulations, kind of a presentation which has a lot of technical details, but I will just rush through them quickly because I know some of you might not have background in the area, but it will give you kind of a feel that where you can really use this multi-scale simulation and what we have really done in the past and what we are currently doing in this area. So that's all. The title will be Sustainability Driven Innovation via Multi-Scale Simulations. And when we call sustainability, or when we talk about environment, then you can imagine that if you only rely on experiments, you need to use a lot of materials, you need to use a lot of experimental facilities, you're using energy, so your carbon footprint is very high, right? So if you use these simulation tools, then you cannot completely eliminate the experiments, but you can still reduce the number of experiments which you need to really develop some material or a manufacturing process. And that's the aim of my group's research, that we develop those kind of tools which can aid those experimentalists. We are not really completely eliminating the experiments. We still need experiments to validate and verify our models. So I hope it works. So as far as myself is concerned, you might have seen who I am. So I am currently at Aberdeen University. If you have ever been to UK or Aberdeen, we are in the northeast of the United Kingdom, and Aberdeen is famous for initially for granite, grey stone, which they used to have, and now it's a kind of a oil and gas capital of United Kingdom, right? So there's a lot of oil and gas activities going on in Aberdeen, and we get the oil out from the sea. So I am here, I'm teaching at a lot of different courses in the area of mechanical engineering. I also deal with employability and skills at the University of Aberdeen, where we try to develop a framework which make our students more employable. So one of my hat is that. I'm also a senior fellow of advanced higher education in the UK, and also a fellow of IMechE and of IOM3. And also I'm a member of an advanced manufacturing leadership group, which is part of Scottish Research Partnership in Engineering and also National Manufacturing Institute of Scotland. My academic background is I did my master's and PhD from University of Stuttgart in Germany and Max Planck Institute for Metal Research in Stuttgart. My track record, you can see I have been working all around the world, so I've been traveling a lot everywhere in the world, and we do a lot of work with research councils, and we do a lot of work at high technology readiness level. That is, we work with different industries as well. As you can see, some of the names are mentioned. So this is kind of my background too and what my research really does. And if you look at my research group, it's the same as the title. We basically work on sustainability driven innovation via multi-scale simulations. And we not only focus on manufacturing, but we also work on design. We also help industries in material selection process, optimizing the manufacturing process, and also if there is a structure already in service, then we also do a lot of work to check the integrity of those structures. So we do integrity assessments as well for the industry. I will quickly go through some of the manufacturing related stuff today because I think you guys are mostly from Center of Manufacturing. So I'm going to focus on that today. So this is just a general outline. I will just go with the introduction. Then I hope you guys have all, well, you know more than me on metal deformation failure mechanism, most probably, since you are an experimentalist. And then I will move from there and I will see how we really take those metal deformation failure mechanisms into our computational model. And I will mainly be focusing on, as Professor Jupiter said, is basically more about crystal plasticity, CP. So I will mostly be focusing on that today. So that's what we're going to do today. So if you look at my research group's low to mid TRL, which is the technology readiness level, we basically work on materials manufacturing. So we develop different types of manufacturing processes, and the idea is basically to enhance the performance of those products which we are making through the. We also do a lot of work on materials during manufacturing. So when we manufacture a component using different materials, how that material is going to behave, what will be their final properties, and how will they perform, right? So we do a lot of work on metal forming, as you see here, additive manufacturing, and subtractive manufacturing, which is like machining processes. From in-service materials performance side, we work on stress corrosion cracking. So your materials or products are always exposed to different types of environments, right? Extreme environments, and they react with that. they can corrode, they can degrade. So we basically model those kind of things as well, and we investigate those kind of things. Nowadays, people talk about hydrogen energy and hydrogen storage. So we do a lot of work on hydrogen steel interaction, and we have developed a model which can predict how the hydrogen interaction really changes the microstructural behavior in austenitic steels. And then we work on other materials like composites and other type of materials as well, which is again out of the scope for this meeting or presentation. So when we talk about metal deformation, I think if you go back to your fundamentals, you will see that your metal can have many different mechanisms. It can have elastic deformation, as you see here on the screen, elastic deformation, which could be twinning, slip-based plasticity. You can have pseudo-elastic deformation if you have a shape memory alloy. You can have phase transformation in the material while deforming. So you can see there is a complex range of mechanisms which could be active when you are forming or when you are deforming a metal. So we basically try to understand which mechanisms are active through experiments, and then we incorporate those in our models at different life scale. And the most important part is their interaction with each other. So how slip really interacts with twinning, or how transformation really interacts with defects. These kind of things really try to investigate and then refine their models. These are some of the examples. You can see this is a more sort of a macro scale model where we incorporated the effect of void growth and coalescence in the metals. In this case, it was aluminium, and we were able to predict the failure in the material. This is a metal ceramic interface. This is a long time ago when I was a PhD student. We did that, and again, this is a single crystal model. So you can see the overall stresses and plastic deformation and which slip systems are really activated, which will really play a role during the fracture. So we investigated that in this case using CP. This is a stress corrosion cracking. So we construct a steel microstructure, which we get from our sponsor partners, and then we expose it to an acidic environment. Material starts to degrade due to the chromium carbide formations, and we try to predict how these cracks are occurring. I hope you are able to see those cracks which are being generated here along the microstructure. So we do that as well. Additive manufacturing side, we basically work on distortion of the components most of the time. So industries and other people come to us and say, okay, we have tried to make this kind of part, but it is distorting. It has a lot of residual stresses. So can you predict it and how we can really optimize the process? So we work in this area as well. This is one of those examples here. I worked on long time ago on ultrasonic consolidation, where you apply ultrasonic energy to the metal and see how you can bond them and create a 3D prototype out of it. So this is another additive manufacturing process where you use ultrasonic consolidation or ultrasonic energy. So these are some of the work we have been doing and we currently are working on. So now let's look at one of the example of sheet metal forming. I don't know which processes you guys really work on. Do you work on sheet metal forming or mostly additive manufacturing?
Yes.
All right. Okay. So it might be useful from that perspective then. So you might be familiar with this process that you can have, you use a sheet, you basically use a die to form it into a specific shape, very simplified definition or naive definition. We also worked with Boeing, for example, in the past, where they said that if we can't manufacture the die, if we are in a region where we don't, because dies are the most expensive part of the sheet metal forming process, other than the presses. So they said we could use some kind of forming tool. We can use a normal CNC to form a component without having a die, right? So we worked on that kind of developing that kind of process as well. That's called incremental sheet forming. So we have basically worked on this different areas and developing models for that. If you now talk about that, we have been working on it for over 10 years now. And if you talk about our models, so our crystal plasticity based models can take into account face-centered cubic crystals, which is aluminium. We talked about aluminium, which has face-centered cubic crystals. You can have body-centered cubic crystals or hexagonal closed-packed crystals as well, depending on your microstructure. So for example, titanium, if it's a dual phase, you can have BCC and HCP as well, right? So depending on the microstructure you have, we are able to account those in the microstructure. You can model a single and dual phase materials now. We can account for grain boundary effects if you already have quantified data. And if there is any loading history, for example, residual stresses, etc., then our models can account for that as well. From fracture side, if you have a ductile failure, you know your voids start to nucleate and grow, and then they start to coalesce. and form a bigger defect, right? So we can also able to account for that in our models. These are some of the examples. As you see, this is a microstructure level failure. You can see how the failure really goes along the microstructure with nucleation and growth. And this is actually the test we have done in the past, and I will show you the example later on, Nakajima test, to find out the forming limit. So this is just a test at macro scale, and we try to compare it with our model at micro scale as well. And these are some of the examples I've shown here as well. If you have worked in the forming limit forming processes, and you might know that you are always looking to predict or understand the forming limit of the component or material, right? How much you can form at different strain levels. And our model is able to predict those kind of forming limits by bridging different length scales. So we have been in this different areas and developing models for that. We have been working on it for over 10 years now. And if you talk about our models, so our crystal plasticity based models can take into account face-centered cubic crystals, which is aluminum. We talked about aluminum, which has face-centered cubic crystals. You can have body-centered cubic crystals or hexagonal close-packed crystals as well, depending on your microstructure. So for example, titanium, if it's a dual phase, you can have VCC and HCP as well, right? So depending on the microstructure you have, we are able to account those, and we can model a single and dual phase materials now. We can account for grain boundary effects if you already have quantified data. And if there is any loading history, for example, residual stresses, etc., then our models can account for that as well. From fracture side, if you have a ductile failure, you know your voids start to nucleate and grow, and then they start to coalesce and form a bigger defect, right? So we can also able to account for that in our models. These are some of the examples. As you see, this is a microstructure level failure. You can see how the failure really goes along the microstructure with nucleation and growth. And this is actually the test we have done in the past, and I will show you the example later on, Nakajima test, to find out the forming limit. So this is just a test at macro scale, and we try to compare it with our model at micro scale as well. And these are some of the examples I've shown here as well. If you have worked in the forming processes, and you might know that you are always looking to predict or understand the forming limit of the component or material, right? How much you can form at different strain levels. And our model is able to predict those kind of forming limits as well by bridging different length scales. So aluminum alloy, if we talk about those, again, I'm talking about aerospace, high strength aluminum alloy here, then we need to first understand, if some material comes to you, you need to understand what sort of deformation mechanism is present, and how does the microstructure really looks like, and how it affects deformation and failure. And finally, what sort of final failure mechanisms were there after looking at the fractography. So we need to identify from this diagram, which I showed you, which are the mechanisms which are really active. So you might, if you have already worked with, if you're an experimentalist and if you have worked with different alloys, that you find out it's a very complex piece of puzzle. You need to really bring those pieces of puzzles together to find out all the answers, find the answers to these questions, right? Through experiments. And once you have done that, then you say, okay, now how I can really simulate and predict the behavior, right? And that's what we really do in my group. So this is an example. So for example, for this case, to find the answer to these questions, we performed a lot of tests, which included uni-axial tests and also sheet metal forming test. We call it Nakajima test. You can see the device here. We cut the samples here. If you look at my image video, you will see some samples at the back as well. Here, somewhere on the side on the wall, you might see some of those samples. So these are those samples. You basically take it to this Nakajima test machine, and you fit it here in this area, and you have these cameras. You use this speckle pattern, which is just sprayed onto it, and you monitor that speckle pattern, and then you find out what are the strains during the deformation through this DIC technique, which is monitored through these cameras. You're always recording everything throughout. So we do that, and we find out, okay, what sort of FLC is there, forming limit diagram it has, how does the deformation really progresses, and where does it really fail, and these are some of the plots of those. So again, we do a lot of testing and find out and come up with these kind of data, and then we start to say, okay, what are the active mechanisms? Another thing is we then go further scale down. So this is all macro scale. You see, we are doing it everything with a naked eye right now and with cameras. But if we have to model at a micro scale, then we need to really look microscopes, right? So we look at the microstructure, we do ABSD analysis, we find out the microstructural data, we do fractography under SEM, and we find out how was the failure really looking like after the failure. In this case, you can see voids are nucleating and growing. These dimples are showing that. So it's a ductile failure, right? So we then identify, okay, void growth and coalescence is one of the dominant fracture mechanism for this metal throughout for different types of loading conditions. So we actually identify by doing all these experiments what are the actual mechanisms, and in this case we found out that, okay, for this aluminum alloy, elastic deformation is there. Plastic deformation is based on slip deformation, slip-based deformation, where you have slipping acting occurring in the material. And then you have some micro defects which are nucleating and growing and then coalescing. And also you have the effect of microstructure orientation. So if your grain is oriented differently from this microstructure, then you will have a completely different response, right? So these are the things which you identified. So once we have identified those mechanisms, we incorporate that in our multi-skid simulation model. So these are some of the equations. I'm not going to bore you with that. We basically have to modify these equations. We have to account for those mechanisms which we have found through experiments in our models, in this complex model, and then we try to predict the behavior. That's what I'm trying to say here. So this is macro scale model at first scale, and in the second case here, we go at a scale down, and we are now modeling at micro scale using CP, and we basically have slip here, which is gamma, the orientation effect, the void growth effect, and nucleation effect, and so on. And we incorporate those in a complex models. We implement these in UMATs, the material subroutines of Abacus. So we interface our code with Abacus, and then we run the simulation. So this is one of the simulation taken from this area of the microstructure, and you can see in this case the failure was occurring in this direction, so we were able to predict that. While in this diagram here, if you see when you change the width of this sample, the fracture direction is completely changed. If you look at here, so now it was initially going in this direction, now it's orthogonal to that, which is this direction. And when we change the loading type, we were able to predict that as well, that the direction of fracture was orthogonal to the previous case. So our model at microstructure level is able to predict that as well. And again, this requires some parameters to be identified. So as I said before, we always need some experimental data to first validate our model and then do the prediction. So this is again the prediction. This was the parameter identification part, as I told you, and this is the Forman limit prediction. So you see these squares are experimental data from that Nakajima test, and these triangles are our predictions using the model which we have developed at microscale. And if you're more interested in the details of the model and the results, then you can look into these papers of ours where we have reported all the data and all the model details are there as well. If you move forward and move from the single phase alloy to titanium alloy, then we are talking about, let's say, dual phase titanium. So when you talk about dual phase titanium, we're talking about maybe HCP and BCC type dual phase material. So in that case, we again account for all those microstructural effects. Again, I'm trying to simplify things for you guys. And after the parameter identification, we are able to predict the FLC, taking the data and simulations from micro scale to macro scale. So although we are accounting for all the physics at micro scale, we are able to predict the macro scale behavior here for titanium alloys. Again, if you're interested in these results or the model details for dual phase titanium, then we have already published that, so you can always have a look. And if you have any question, you can always come back to me. Nowadays, what we are doing, we are working on another new alloy, which is metastable beta titanium alloy. In this case, if you remember previously, we only had slip, elastic deformation, and crystal orientation effects. Now we are also accounting for transformation induced plasticity. So this metastable beta titanium alloy, when you start deforming it, it transforms from BCC to some other crystal structure, BCT structure, right? And we need to account for that. Again, this is a collaboration with Professor McMeeking from UCSB. University of California, Santa Barbara. So you can see again we have developed the model. This is the case of stationary crack, and you can see how the transformation really influences the crack behavior in this case. So we are investigating that. Also, there's a high potential of this metastable beta titanium alloy to be used in stents. So we are able to show that these stents can really use or exploit this transformation phenomena, which is happening during the deformation, and we are able to predict that behavior as well. So this is another example which I wanted to give you from titanium perspective. Okay, this is again a dual phase. So we have BCC and then it converts to BCT. So in general, we have a multi-scale computation framework, which can account for different types of crystal types, microstructural effects, and also defects. And we are able to predict at different length scale how does the material is going to behave, whether it's a single phase material or a dual phase material. Yeah, so again, you can find some data, some stuff here. And also what we are trying to do now, everybody talks about data, so big data, data-driven machine learning. So what we are trying to do here is, since, as I told you in the previous examples of these models, these are very complicated equations. And I'm just giving you some of those equations here. If you look at the paper, you'll find there are hundreds of equations there. So to derive all the things and implement them in a computer code. So what we are trying to do now, we are trying to move from those simulations, because they are sometimes slow and sometimes they are very complex to handle. So we are moving from those physics-based models to the data-driven computational frameworks. So we generate the data from experiments, and then we generate additional data from our models, which can support this data-driven computational framework. And we are trying to predict these kind of material behavior. So again, if you're interested in that paper, you can find more details in this article. As an example. Other than that, I mean, this might not be very relevant to you, but we do a lot of knowledge exchange activities. When we say knowledge exchange, we do a lot of work for locally and also. So we call that work as mid to high TRL work. So what we are trying to bring is, we are bringing our research from fundamental concepts to an applied level, so that industry can really use it, right? This is what knowledge exchange activity is all about. So we have a lot of industry funded projects in the area of advanced manufacturing. We work on offshore decommissioning monitoring. So we have a national decommissioning center at Aberdeen University, since everything is oil and gas. And you might have seen a lot of oil platforms in the sea, and some of them are already coming to their end of life. So they are now thinking about decommissioning them. So we have a national decommissioning center. So how to monitor those decommissioned assets is one of the projects we work on. A few projects we have about that. Hydrogen storage challenges. I'm currently working on 2 different projects related to that, and with some local industries. And also we work on digitalization of fitness for service assessment. So any structure which is there, and if you want to really see what's going to happen to it, or if something is going to happen to it, so we develop kind of digital twins for those kind of structures. And this is one of the example here. So this is a cross section of a wind turbine blade, and in this case we developed a kind of a failure envelope for a blade which was used in a wind turbine and we were able to show that, okay, which areas, if you find a crack, where you need to really stop everything and do something about it before you will have a catastrophic failure, right? So we work in this area as well, so to have industries and digitalize their fitness for service assessment, rather than they just do the inspection and they have no idea, so they send the data offshore, and then it takes a lot of time, and before that you might have some accident. So to avoid those kind of things. So these are just some of the acknowledgements with which we have all collaborated from the perspective of advanced manufacturing related stuff. And yeah, that's what I wanted to summarize in this quick time. So I hope you find it useful and it was not too complex, but the idea is we have crystal plasticity based models, which are generally user material subroutines, UMAT, and they are interfaced with Abacus finite element software. So we can model single phase and dual phase alloys, whether they are FCC, BCC, or HCP, crystal structure.
Yes, Mohammed, thank you very much for this presentation. It's very interesting because I got last time, 10 years back, we have got the increased space capacity of 7 and then we reduced to 3 to get this vital state and so on. Yeah. So and then you continue with the crystal plasticity and this I become this perspective. But what we have done is very interesting. So what I was saying is that the hydrogen use tracking.
Yeah, okay, good.
So you are doing for, or you have done for the sensing, right?
Yeah, so we have worked on austenitic stainless steels. So the material was basically theirs, and we took the microstructure, and I might have a slide on that. In any case, I mean, you might see it here as well. So this is one of the examples. So we use a microstructure here. We had a microstructure here, and we basically use that for this. Yeah, so you see this, these are the same microstructure with 3 different hydrogen concentrations, and the microstructure is showing very different response. See, in this case, when you have 0 hydrogen, you have more ductility as compared to as your hydrogen is concentration is increasing from 0.0 to 0.35, 0.64, you have a very different response. And we basically, so in this case, the main mechanism was that the hydrogen basically diffuses in the lattice spaces, and then they start to apply, diffuse around and go to the interstitial sites, and that causes the change in the material properties, and we accounted for that in our model. If I can find the presentation, that would be great. Like, give me a minute. We do a lot of work on biomechanics as well, but so here you might see some. So for example, if you can see, you see these new slides here now. So we did work with three or four. I don't know if you can see the slides. Yeah, 3 or 4 austenitic stainless steel, and where chromium carbide really make these areas around the grain boundaries to be brittle. So we basically modeled that, and we were able to predict the crack length as a function of exposure time for this kind of test, which was a double band beam test performed in a HCl environment. So this is one work we did, and the one which I showed you just now, we have hydrogen, which basically atom which resides in the interstitial lattice sites or traps, and they remain in equilibrium. And for this case, we try to understand the effect of those hydrogen in different locations in the microstructure, and we were able to. This is the animation I showed you for 3 different concentrations, and you can see the microstructure is shown here on the right hand side, which is just a representative to show how the model value works. And you will see a certain amount of time that the one without hydrogen has more deformation as compared to the others. And you can see the grain boundaries and all these things here. So again, we account for different types of behavior as well. If you're interested, again, the paper is published. So yeah, so also we did the effect of hydrogen on void growth. So if you have a defect, then how does the defect under the loading behaves if the hydrogen concentration is changed? So we also investigated that, and we reported some very interesting results that some people report that maybe hydrogen, these voids, because sometimes you find out that this hydrogen-induced cracking is more brittle in a way. And we try to prove here, we try to show that even though you have some voids there, but this hydrogen concentration really restrict the motion or the expansion of these void or growth of this void. That's why you don't have a ductile failure, you end up with a kind of a brittle failure as well, relatively brittle failure. So again, the results are published, so you don't have a look at that. So yes, we did some work, but it's mostly steel, and it was austenitic steel.
Yes. We are actually quite focused on my this student here will be focusing also combining this Crystal Plasticity. And then have you done any research on that? By using and combine with the Crystal Plasticity? Already started with this research for this still in the progress.
So which model you're talking about? Is it the neural networks you're talking
about? Yes, correct.
Yes. No, we currently haven't done anything related to neural networks. I did one project with the guys from, I think one was from Belgium and the other one was from Canada. And what we did in that case was, they basically they wanted the data, right? What you need is the data to predict anything. And it depends on what scale you really work on. So what we did was, we developed the data for them. And the data in this case was strains, stresses, and also in that case, it was an FCC material. So all the slips in the 12 slip systems, right? So we need that kind of data to train the model, because there are no equations for slip or anything like we have in our models here. For example, so here we are predicting this gamma, which is the slip, which is acting due to the dislocation motion, etc. but data-driven models don't know anything. So depending on the length scale you work on, so if you have the data for stresses, strains, and slips, etc., then you can use that data to train ANN or any other neural network or machine learning model or deep learning model to predict the deformation behavior. So in that case, I think they were trying to predict the rolling behavior of aluminum alloy. So they were rolling it, and they were trying to predict the microstructure orientation changes and all these kind of evolution basically during the rolling process. So I don't know how far they went along. We just generated the data and we gave it to them.
And the data is experimentally obtained.
No, they had experimental data, but experimental data has limitations. You can't really capture the real-time activity of all the slip systems, and also the grain reorientation and rotations, etc. So we use a model, because model can give explicit data at each time step, right? So we develop the data at each time increment, and they use that data along with their experimental data, as I remember.
Okay. So you are doing physics.
Yeah, exactly. That's what we did, because we only work on projects where we have funding for, right? So that's how it works on this part. So we currently don't have any funding in that area. So we do work on different machine learning tools, but we work at a macro scale. So we use FNN, we use ANN, we use CNN, convolutional neural networks, etc. So we use different types of neural networks, and we do also random forests, and we use SVM we are using to predict different types of behavior as well. So again, those are all macro scale, not micro scale. So it depends what you really want to do. We can do that.
Okay. So we are also going to start with this. So is it possible that we can collaborate in these directions in the future?
Yeah, sure. There are usually we see a lot of calls coming with the joint UK Malaysia proposals, etc. So hopefully we can do something about that. If you guys have some internal possibilities, then we can also write some projects, and we can jointly supervise some PhD students, researchers. It's not a big deal.
It was called last year, I think, Newton grant, something like that.
Yeah. Even if you have some internal funding which supports your PhD students, I'm still happy to collaborate, and we can do something together.
Thank you very much. So another one. Do you still have 5 minutes?
Yeah, it's okay. I have time until 11, so that's fine.
Southeast Asia, we have also a lot of oil and gas.
Yeah.
So you have written that you have focused some projects in the oil and gas decommissioning.
Yeah.
What kind of activity are you doing there?
Yeah. Okay. So we do a lot of work. As I told you, we have a national decommissioning center. So we have because we take the oil out from the North Sea, because we are next to the sea, right? And after a certain life of these wells, they have to decommission according to the regulations. They have to remove the stuff from the sea and make it clear, so that it's environmentally clear and there is no impact on the environment later on. So what we do, we basically work with the industries to come up with developing different types of frameworks which can tell them or guide them that how they can remove the stuff from the sea without impacting the environment, and if they leave something behind as per the regulations, when to monitor and what to monitor as well. And in this case, what I do from my perspective is, because we have a team of people who work on risk and reliability, safety, etc., and chemical side as well. So I work on the long-term degradation. So for example, if you have a steel which is in sea environment, you can have microbially induced corrosion in the material, right? So we work in that area as well. And so we basically do some kind of modeling, and we do a lot of other things as well to come up with kind of a guidance for the industry. So this is one of the example I wanted to give. Other than that, we also do a lot of things. For example, if industry is coming across some kind of defects and they want to see these defects as stable, they want to do something about it, as I gave you in this example of the wind turbine blade, then we can do complex calculations and simulations for them and come up with some kind of failure envelope or a code which can help them make a decision that is it safe to operate, or is it we need to stop it to avoid any catastrophe, etc. So we develop different types of digital twins as well for business services. Okay, so we do a lot of work with the local industry as well. If I have some slides, I can show you some examples of that as well. So this is one of the examples we see. We in the oil and gas industry, they talk about API 579 design standard, and it's a very complex document. There are thousands of pages of document and a lot of complex calculations are there. And at the end, you also need to do FE analysis if it fails at different levels. So we have automated this process for one of the industry, which is mentioned here. So everything for part 4, which is the like you have a localized corrosion defect, or if you have a general corrosion in your material or structure, then we can assess that automatically with just a click of a button. We have a software for that and app we have developed for that. And if it requires FE analysis, then the code based on the geometrical data, it can automatically generate the input files, abacus input files in this case, and it can run the analysis and it can generate a report for you for the industry automatically. So these are some of the aspects we are working on. So that's an example. Other things, as I told you, for these data-driven approaches, we haven't gone up to the micro scale, but whatever funding we get, we work on those projects. So this is one of the example of the wind turbine blade damage. I gave you that example before as well. So we use different techniques, KNN, SVM, and FNN, predict the damage in the wind turbine blade. Also for predicting the microbially induced corrosion, as I gave you for long-term duration, if your structure is basically exposed to subsea environment, so there are many microbiological organisms there as well, so we are able to predict that as well. So you see 2 dots and are the actual one and the other ones are the predicted. Also we did this project with Jiangsu University in China, and they wanted to predict the elastic properties of metamaterials. So again we use deep learning to predict these elastic properties. This is stress corrosion cracking. Again, from those complex equations we move towards predicting it at a micro scale. So this is the CPFAM simulation data, and these are the machine learning simulations, and you can see they are matching really well after training and testing. So we do a lot of work at micro scale on these as well. And if there's an interest, definitely we can collaborate.
Okay. So it is interesting. Yeah? In Europe, they trust already the simulations. Here in Southeast Asia, still yeah.
As I said, first thing is, the people are obviously resistant to the change, and that's why at the start I always emphasize that we are not taking things away from experimentalists. Experiments will always be there, and that's truth. That's the truth. It's just that we are trying to reduce those number of experiments through these simulations. We are not completely eliminating experiments because the experiments are required to validate the models, and the more data you will have from experiments and from your simulations, I think it will go in a more positive way.
Yeah. So another topic which is very hot here is the carbon capture, but not in the mechanism to capture in the side of the storage. So you have said that you have done some projects in the hydrogen storage things there. Do you have also any experience on the carbon capture storage, something like that?
I directly haven't worked on the project, but I know some of the colleagues here who they are developing developing different types of materials, concrete-based materials and biological materials, which can basically absorb carbon and utilize carbon to bring the net carbon to zero. And some of them are working on carbon and hydrogen, carbon storage as well. We are currently working with an industrial project, which is all about hydrogen storage. And what we are trying to see is if we can use the existing infrastructure, which could be oil and gas structure, for hydrogen storage, under the sea, or even using the same infrastructure which we already have there. So there are works going on, but again, these are currently not at a higher TRL, which is the technology readiness level, in my opinion. So we need a lot of work to do in this area.
Because Petronas has also they cannot be up there something like that. They also actually trying to fund the universities research in carbon storage sector. Yeah. So is it possible that we can talk with them?
Yeah. If you can send me some more details, and if you have some calls or some idea details there, then I can connect you with the relevant people as well. That's not a big deal.
Okay. Yeah. Nice. Yeah. I will here.
Yeah.
Oh. So last question. I dealing with the phase transformation model.
Yeah. So when we talk about phase transformation, there are two ways to define it. One is the thermal phase transformation at high temperatures, those phase diagrams we have. And the other one is the mechanical transformation. So we currently work with the mechanical transformation, which is generally termed as a transformation induced plasticity. So for example, I gave you one of the example at the end with for the metastable beta titanium alloy. So that metastable beta titanium alloy, which is used in aerospace and biomedical industry right now, has a feature that at a room temperature, when you start to deform, its BCC structure starts to change or transforms to BCT structure, right? And the whole deformation mechanism and deformation chemistry changes. And that's what we are trying to do in our modeling. And we have captured or included that. So if you remember, this is the example which I was giving at that time. So we have, so this is the transformation induced plasticity, which is based on the fact that this BCC material is transforming to BCT. If you look at the microstructure, I don't know if I've shown you here, yeah. You have alpha and beta matrix, and this beta is metastable. And that really starts to transform during the deformation at room temperature. So what people have done, this transformation without slip improves the ductility, right? So you can form it more, right? So we are trying to see how we can exploit this transformation to basically improve the ductility or formability of this material. And that's what we have done in this work as well. And you can see we are able to capture that. Also, it is used in the landing gear. One of these 1023 alloy, which is a metastable titanium alloy, is used in the landing gear of one of the Boeing aircraft. So in that case, if it generates some kind of fatigue cracks, then how these cracks will interact with the transformation induced plasticity. In this image, in this animation, that's what I'm trying to. So we do work, but not at the high temperature transformations, which is, I think, this area here in this diagram, but rather we are working on the transformation induced plasticity, which is based on this, where the structure changes, crystal structure changes due to the deformation.
All right. Any other questions?
If you have any questions later on, please feel free to contact me, and I'll be more than happy to answer.
Yes, it's also a good idea. Because here in Malaysia, we are actually pushed or forced by the community to have international collaboration, joint publications, joint supervision. I don't know whether in Aberdeen also the same.
It's the same everywhere. I think we are always asked to basically collaborate as much as possible. And even if it's not the case, I always try to collaborate as much as possible all around the world. That's why you see my list of collaborators are very long.
Yeah. But yeah, once again, for example, we would like to this
Good.
I hope you are also willing to guide us.
Yeah, sure. Anytime. You guys can be in contact with me anytime, and we can, if you have any ideas, we can always try to simulate and see what we can do together. So I'm always open for everything.
Okay. From Amir, I don't think that they have questions for you. So I would like to thanks once again.
No problem.
In the name of here. And then thank you very much. And then see you later.
Okay, thank you very much everyone for attending my boring presentation. Enjoy your time. Okay. And
All right.
we will be in touch. Bye.